It's with great pleasure I now turn this special session over to Ian to begin. Ian?
Just a brief overview of the agenda and what we intend to cover today. So a high-level overview of each of the individual slides. So first off, because it's so important in the nature of these type of PCBs, is a review of the transmission line theory and the different dielectric materials that are available. We have a look at the passive component selection and the best practices with regards to that. A brief look at the capacitors, which ones are better for RF circuitry, which ones are better for low-pass filters. Then a look at inductors and what are the critical components and critical specifications to keep in mind for inductor performance. Then a look at resistors and how do they behave at high frequencies. A brief look at transformers. Then a look at phase lock loops, and I guess to explore the inner circuitry of a phase lock loop and identify what's sensitive and what we can afford to perhaps not give high priority to. I look then at oscillators. Voltage controlled oscillators would be the primary focus, so we look at the best practices with regard to layout, tuning voltage, the power supply regulators, and when applicable, shielding. And then look at crystal oscillators, so we look at what considerations to take into account for the output type, whether a square wave or sine wave is preferable, and whether clipped is preferable to both of those. Then we brief look at power regulators because they can have a big importance, I guess, on the phase noise of the PLL system. And then, given that there are so many different nets, different traces coming into a PLL, which of those is critical? And we finish up then with a worked example using the ADIA 4356, taking into account everything that we've learned. A brief look at a strip line transmission line, so in very multi-layer printed circuit boards with more than 4 layers. You have a layer of ground and overhead and beneath the signal conductor. So what we see here is that this trace here in the middle is carrying the signal and it has great isolation, but it does require ground planes on top and bottom, which is expensive. And also, to get from the top of the PCB to the bottom of the PCB, a lot of vias are required. Double vias then are recommended to reduce the loss due to discontinuity. Line and the coplanar waveguides. So we tend to use a lot of these on our boards, which we give out on the customer evaluation side. So the microstrip is quite a simple transmission line with just signal on top, a dielectric in between, and then a ground plane underneath. So this is quite simple, easy to fabricate, and it doesn't require many vias. However, as we hit millimeter wave frequencies, as we approach tens of gigahertz, we find that these type of microstrip transmission lines cease to be useful and that they're too lossy above 30 gigahertz. And differently, then we look at coplanar waveguides or grounded coplanar waveguides, which bring a ground plane to either side of the signal on the top layer, and then depending on whether it's the CPW or the GCPW, there will be a ground plane underneath. And in this, the thickness of the lines and the thickness of the gap between the signal line and the grounds is what makes up the characteristic impedance of the lines. We won't dig into the fabrication of these, but there are tools on the web to help actually design the correct spacings of these transmission lines. However, coplanar waveguide is more difficult to manufacture. The thicknesses are more critical and the gaps are more critical, so it is more expensive. We need vias on the top layer to a ground at the lowest wavelength, so that would be the highest frequency. We calculate what the wavelength is for that and divide that by 4. So there tends to be a need for quite a number of vias on either side of the ground coming up to that signal trace on top. There is lower losses at higher frequencies compared to microstrips, so they have advantages over the simple microstrip line on the left-hand side. And also they are a little bit smaller, so the physical size of these is smaller. The signal conductor can be smaller than an equivalent for microstrip. and it has better isolation because of the ground at either side of the signal, and these are still useful above 30 gigahertz. To get an actual measurement, the left-hand side shows the insertion loss of a microstrip line, and the right-hand side shows the insertion loss of a grounded coplanar waveguide. So both of these are quite good down at 250 megahertz, which is the start of our S21 plot here. But what we will actually see is as the frequency increases, as we hit about 60 gigahertz, 50 gigahertz, the loss on the microstrip line is about 6 dBs, and the loss at the grounded coplanar waveguide is about 3. So there is an advantage with the grounded coplanar waveguide, and this is considering the same dielectric and PCB stack-up. So it is a direct comparison between the two technologies. Then, let's say, routing these high-frequency transmission lines, it is important to be gentle, I guess, with these transitions. Let's say, as a microwave frequency goes from one line thickness to another, it's important to try and make it as smooth as possible. So on the left-hand side here, we can see a nice smooth taper, which is the best practice for a microstrip taper. Not as good as that, but reasonably okay is one where we have steps going from one thickness to the next, and then finally, not recommended is an abrupt change. What will happen is signals will actually begin to bounce back at the transmission point, almost as if this was a 4-lane motorway going into a 2-lane motorway. Considering then the corners, where we have to route the microstrip frequency around a corner, again, an abrupt 90-degree turn, if we have it in a square, like it is here on the top left, that's not good. And then as we kind of taper it a bit more, let's say we kind of make these corners a little rounder in some cases, although there is a rule here for the best one, which is to kind of follow this equation here for the thickness of S and D, and to keep the ratio between these at a value of 0.7. This is the best 90-degree turn that we can make on this. So changes in the line width should be gradual rather than sudden, just to reiterate what we are saying. And if bends are unavoidable, then follow the guidelines. So looking at vias and bringing up in more detail 3D electromagnetic simulation, what we see is how important it is to have the ground return vias on any transition from one layer to another. So it's especially important for layer-to-layer signal transmissions through a via, and it's important to minimize the return current flow path. So every time a via is utilized, a ground via should be utilized next to a signal via. This allows the current to flow near the signal current flow, but the signal via flows through essentially a cylinder that wants to have the return current flow 360 degrees around it. So if a single ground via is used for the return current, the characteristic impedance of the trace will be altered slightly and may be an issue. So the signal traveling in the z-axis from the middle of the board up to, let's say, the top of the board, it must have a reference ground return located nearby, ground return via located nearby. So figure 5 above shows the return current density in a signal transmission via with a single return on the right-hand side versus 4 return vias on the left-hand side. And notice that the circuit with 4 return vias has less current crowding in the return path and the transmission path. Difference in PCB dielectric materials. So FR4 is kind of the cheap and cheerful material for a PCB dielectric. But above 3 gigahertz, we find that the losses of this per inch, in dB per inch, begins to increase. So you can see the purple line here is for FR4. Rogers 4350 is a better material. So this one is coming up around here. So we have considerably less insertion loss at 18 gigahertz compared to FR4 per inch. So that's a relatively inexpensive option, but for some applications we may require some lower insertion loss like Rogers 4003. That has very good performance, but it's not the best. The best is Rogers 3003, and that's the most expensive, and it might be difficult to source at the moment, but I think maybe that this slide needs updating. So a brief look at isolation techniques and the methods. So grounded coplanar waveguide is better than microstrip, as we discussed earlier. And as the animation shows up here, the isolation is provided by the ground to either side of the signal line. A strip line is better than either, so that's the first transmission line we showed at the beginning of this presentation, where we have a ground plane over and below the relevant signal. We can increase the physical distance between the signals. Now, there are practical limits to that, but it is a good idea if it's a critical isolation specification. We can minimize the ground loops, taking care to ensure, in the example where we had the via, that the grounding is kept very close to the signal in question, close enough, let's say, to obey the transmission line characteristic impedance. RF shielding can be employed, so we can have what we call metal cans over circuitry, like we have here on the right-hand side. And in this case, we have 4 shields around each of the PLL VCO circuitry to minimize the crosstalk between them. Differential signals can often be employed then for lower frequency lines like the reference, where we might be able to eliminate any common mode unwanted signals that appear in each of those lines. A shielded module then can be used also, let's say, in the case of the standalone voltage-controlled oscillators. These are often fully encapsulated with shields below and above their sensitive circuits. And finally, on a PCB itself, we can use isolation slots and apertures, which help increase the isolation. Moving on to the passive components, the placement of them and the choice of them. First off, so looking now at capacitors. So single layer capacitors or thin film are very useful into the microwave range. So if this is something like a harmonic filter or a DC blocking cap where a high frequency is being passed through it, then it is important to choose the right capacitors. So thin film capacitors are very useful. We can consider electrolytic or tantalum capacitors, but they're not really suitable for the high frequency applications and are preferred, I guess, for power supply decoupling, where we're more interested in audio frequencies. But these capacitors do not have the right characteristics above 1 gigahertz. Smaller footprint capacitors tend also to have lower parasitics, so we notice that 0402 is preferred to 0603. And what we see here on the right-hand side is the equivalent circuit. So what we will see is there is the nominal capacitance in series with a parasitic resonance or a parasitic inductance, LS, and an effective series resistance, also with a parasitic parallel capacitance. So manufacturers tend to provide models for RF simulators like ADS or ANSYS, and Murata, among others, do have very good models. And we do recommend that we only use RF rated capacitors above 3 gigahertz, especially for matching circuitry on some lines. And it's worth checking to see if a simulation model exists for critical high frequency lines. We often say never to take anything for granted in RF and microwave. And sometimes we say this is the reason why some of the best RF engineers are rather cynical. A brief look now at inductors. So these can often be the most problematic component in RF and microwave circuits. So these have lower self-resonant frequencies than most capacitors, and high Q wire-wound inductors then are easily sourced for greater than 1 nanohenry, but anything smaller than that will require a PCB trace to be used to try and generate the necessary inductance. What we see here on the right-hand side then is the equivalent circuit, and you can see that it has the nominal inductance, and that's in parallel with in parallel with a resistance and also with a capacitance. All right, and this is what introduces the resonant frequencies. Then there is also another series resistance to consider. So more on inductors. Then if we use an inductor to complete the VCO tank circuit, then a high Q is absolutely essential because that will have a strong bearing on the VCO phase noise. Also, we need to ensure that no mutual inductance affects the nominal inductor value. So what we will see here, and on the photograph on the left-hand side, we see that the inductors are placed close together at right angles, and this minimizes the mutual inductance between them. So what we did in this example here for the ADF 4360-7 is we had two external inductors connected to complete the VCO tank Q, and these are placed at right angles to one another. In some cases, inductors can require shielding, and that's because inductors can sometimes pick up stray signals from some circuitry like a power amplifier. Considering then resistors, so resistors we could probably consider to be the most well-behaved of the lumped components at microwave frequencies. And a good RF and microwave resistors are designed as such, and especially with regards to trim. What we'll see is that a traditional helical trim can add inductance, and to consider the equivalent circuit model, what we'll see is there is a shunt capacitance on both of the pins. The input and the output of the resistor will have the nominal resistance itself, a parasitic inductance in series with the resistance value, and then a parallel capacitance. What we notice is smaller footprint inductors have lower parasitic behavior and are more suitable for higher frequency applications. Moving ahead then to phase lock loops. So considering, what we need to do, then what do we do using a phase lock loop? So phase lock loops have lots of digital blocks, at least some of the more common ones that exist in the ADI portfolio. So they will emit spurious at the PFD frequency, which we need to be careful of. If they're fractional N parts, then these will have sigma delta or delta sigma modulators, which require K-fold treatment to ensure low fractional spurious. The MUX signal, so most of our devices have a pin called MUX out, which is usually used to access internal parts of the chip, and these can be very useful for debug, and you can access the reference counter or the feedback counters out, but typically that's another signal if you turn it on. So we recommend only using it in debug and not using it or leaving it on when you actually have the system running in an application. The charge pump output then needs to be kept from the other sensitive line, so care needs to be taken with that. We've more on that in a minute. And we also should take care with the digital SPI lines, because if these are being programmed very quickly, these can sometimes be picked up by some of the rest of the circuit, which we don't really want. Interface. So on the previous parts with a 3-wire interface, we call these pins clock, data, and load enable. On newer parts, we call them S-clock, serial data input out, and convert start, or CSB. The voltage levels required for programming the part are CMOS levels and can have clock speeds up to 50 megahertz. So if something's running at 50 megahertz, chances are it can couple in. And poor layout can lead to this SPI clock actually coupling to the LO output. So what we have on the left-hand side is the top layer of PLL showing two pins. One of those is the RF input, and the other one is one of the SPI lines, and that's on the top layer. But if we dig into the layers underneath, what we'll see is that we're routing the clock, data, and load enable lines right underneath that sensitive area where the RF input is. So we realized pretty quickly that this was going to degrade, that this was going to couple onto the RF line. So we recommended to move those traces away from that critical RF input. And ideally, digital signals shouldn't be close to RF lines without sufficient isolation. Low pass filter, so these need to be kept somewhat isolated from other signals. Obviously, it's easy to do it with just a PLL board. Sometimes if space is tight, compromises have to be made. But loop filter components, certain components are better than others, so COG type capacitors are preferable to X7R. So we notice that X7R capacitors can sometimes have piezoelectric effects when the temperature changes rapidly. So the COG type is preferred as they do not have this issue. So if we look here at at a photograph of a PCB, we will see the VCO and then a rather elaborate arrangement of the low-pass filter coming from the IC chip here on the right-hand side of the photograph into the charge pump, and then coming in through the inductor here, because this low-pass filter has an inductor in it, and then before it drives the tuning port of the VCO on the left-hand side. And in critical lock time applications like the fast locking ADF4193, which is in the example below, COG type capacitors are essential. Worth noting that ADI Sim PLL, our free PLL simulator, fully supports the ADI PLL portfolio for frequency and lock time parameters, so you can get a good estimate of how the low pass filter will perform by simulating it using this tool. The voltage controlled oscillator, so typically a quite simple circuit, a power supply, the RF output, and then a port which we feed with a tuning voltage, a DC tuning voltage, and typically quite simple, but there is quite a sensitivity to V-tune. So V-tune is what sets the frequency, so any additional noise or spurious that appears on this line will also appear in our RF output, so we need to be very careful of that. For this reason, because of the sensitivity of a voltage controlled oscillator, we tend to add a lot of shielding to the VCO itself. So you can see from other manufacturers like ZCOM, they actually have a kind of encapsulated shield over the VCO circuitry. Something to be careful of is a thing called injection locking. So if we have a very strong tone coming from a nearby circuit, it can sometimes lock the signal unintentionally. We have more on that in another slide. So considering the V-tune line, so V-tune probably is one of the most critical lines in a PLL system. So we have an example here of a photograph on the left-hand side showing a PCB trace. And the mantra we have is that if the V-tune line is incorrectly treated, it can pick up digital signals, the reference, or any other signals which modulate the tuning port of the VCO, which can increase noise and spurs on the output of the PLL. So the example on the left shows the V-tune line, which is after R17. And a number of errors were made. So first off, there's a line connected to an external SMA. So there's an additional trace on the output of this V-tune line, which is going to pick up extra interference. But the extra track then could result in an added interference coming from the additional inductance that exists because of this extra trace. Also, there is a test point on the line which can add noise, or any spur signal could be coupled in because a test point can be considered to be a mini antenna, which, if incorrectly laid out, will pick up an additional signal, which we don't want. Now, the case could be made for the inclusion of a test point in the case of a debug on an evaluation board, but the eventual outcome for this was we did remove the SMA with the additional trace, and this reduced the PFD spur on this particular board layout. For customer convenience, we made a decision to maintain a test point in some boards, but in most of our customer designs, it's eliminated wherever possible. And care should be taken to ensure that the V-tune line is kept short and simple. Considering then crystals and the reference sources. So there is an option to use differential crystals, which can be preferred for lower electromagnetic interference, but they're not very common and they are more expensive. We do find then that a square wave can be better for phase noise, so in that case that it has a faster or a sharper edge with respect to time, but a square wave will have more harmonics, and these can be more problematic to filter or remove from an RF system. A sine wave can be better for EMI and related spurious, but it wouldn't have as fast an edge as a square wave. And a clipped sine wave then is a good compromise between the two. So considering in more detail the PLL reference or ref-in, what we show here on the left-hand side is a PCB trace where we took care to isolate the ref-in, which is coming in through test point T2 and the capacitor C10, and the circuitry beneath, which is capacitors C12 and C26. So in a PLL reference, the signal can be either a clean sine wave or a square wave. More usually, it can be a clipped sine wave from a TCXO. A necessary precaution is to try to isolate the ref-in line from the RF line, so that we want to minimize coupling from the reference to the RF. Generally speaking, the ref-in is not a desired signal to get onto the RF line. So coupling to the VCO or the RF-in can increase spurs and violate specifications. And this is particularly important if a square wave is used, as the harmonics of the fundamental could easily couple to the RF lines. So looking then at the ref-in of an ADF4360, now injection locking is rarely an issue with discrete synthesizers like the ADF4113 or the ADF4106. However, in extreme cases, a poorly routed board may suffer from injection locking, and a number of factors can influence this. So if we have high reference frequencies with high slew rate, so square waves, as we discussed, and looking at the printed circuit board file on the right-hand side, we can kind of see this was an earlier vision of the board we discussed in the previous slide, with less care taken to isolate the signal coming in the test point on the top right-hand side of the trace and the decoupling capacitors to the VCO circuitry underneath. So if there's a low overall frequency multiplication factor, so if the VCO divided by the reference is a small number, 60 or lower than that, and if the layout then isn't very good, all of these factors can combine to create something like injection locking. And what can happen is those above conditions can cause the unwanted frequency, in this case the reference input, to couple into the VCO circuitry through the decoupling capacitors to the VCO circuitry underneath. So good layout is essential to avoiding the problem, ensuring the isolation is between the reference and the CN pin in the case of this particular device, but any of the specific VCO decoupling capacitors on some of our integrated PLL and VCOs. So on the 4360 evaluation board that we designed, we did not see the problem, and to duplicate this on our PCB setup, we actually had to solder in 4.7 picofarad capacitor between the ref-in line and the CN line, and that showed, I suppose, that we could create the path for that particular problem. What we see is there's the ref-in pin in pin 16 with the arrow pointing to it, and below it there in pin 14 on CN, and that the digital ground trace in between, which provides a measure of isolation, should be kind of increased between these to improve the isolation. So considering now power supplies and regulators, so in general we do recommend using low dropout regulators or LDOs, like on the left-hand side there, the ADM7150. Switching regulators like the ADP2370 can be used, but caution is advised in the case of the VCO or the PA picking on the stray switching signals that come from the switcher. For our VCOs, and especially the wideband VCOs, the choice of regulator and the noise performance as such can have a critical effect on the performance. So for the 4355, 5355, we recommend the ADM 7150 or 7170 low noise LDO. And the VCO pushing, which is on the datasheet spec, this indicates the sensitivity to power supply, and lower is generally better. The ADP 150, to give a comparison, gives about a 4 to 6 dB better phase noise at a 100 kHz offset compared to the ADP 3334. An example, the routing priority, like how to start. So first off is identify the most critical traces. So those will be the RF output or the RF input lines, the high frequency lines, like either the output of the VCO or, where applicable, the feedback to the PLL end divider or RF input. The V-tune line, which is the filtered charge pump output, is the next critical. And then some of the power supply lines, like the charge pump and the VCO supply lines, are the next most critical. Then the PLL reference input, we've got to take due diligence with that. And then we see the analog and critical digital supply pins. Some of these are more important than others. Reading through the data sheet will help you identify which ones are. And then we talk about the other digital pins, like maybe the SPI lines, and finally the ground. And again, not all grounds are created equal, so short trace to the ground plane is best, but the high-speed circuitry gets priority. Example then using the ADF4356. So we start with the RF output traces. Let's say we're laying out a board and we're carefully building up the PCB. So this part, the ADF4356, has got 4 RF outputs. A customer using only 2 can afford to prioritize only the 2, but this part is 4, so we give our customers access to the 4. So first off, we route the trace from the output of the pin of the ADF4356 to the edge of the printed circuit board, and these take the highest priority. Then we add the VCO supplies, we add the V-tune, and we add the reference. So we're kind of building up, I guess, all of the circuitry around the PLL. Then we go further, we start to add in the remaining supplies and some of the analog traces. So now we've built up a more complete picture of the circuitry around the ADF4356, and we start filling in some of the surrounding circuitry then as well. And finally then, all of the traces are placed, so we've kind of jumped forward quite a bit, I suppose, where we've added in all the digital pins and the grounds and the vias necessary. But this is kind of the path we would recommend customers take to build up an effective high-performance printed circuit board for a phase lock loop. And more of our webcasts are available at the links highlighted here. Back to you, Chris.
All right, thank you, Ian. So, our first question for you, Ian, what care should be taken with the PLL reference?
The biggest care to be taken with the PLL reference, I guess, is that it isn't routed too close to the VCO. So the one case we identified, which was particularly bad for the PLL reference, is one where it can somehow get right into the voltage-controlled oscillator and create a kind of a competing locking mechanism known as injection locking. I guess other considerations would be to make sure that the reference isn't picking up anything else, because if it picks up, another unwanted frequency, then this could end up appearing on the PLL output as well. So mainly keep it away from the VCO, but keep it out of harm's way as much as possible.
All right, thank you, Ian. Our next question for you here. On a voltage-controlled oscillator, what's the most sensitive line?
Well, care should be taken with all the lines on a voltage-controlled oscillator, but the V-tune line merits particular attention because this is a DC line which directly modulates the variable tuning frequency element of a voltage control oscillator. So if there's any unwanted frequency tones appearing in that will appear as a spurious tone modulating the RF output of the VCO. Now, having said that, care should be taken with the power supply as well to make sure that the regulators are of sufficient quality and that we're not modulating that with an unwanted spur tone either.
All right, thank you, Ian. Looks like we have time for just one more question here. Which type of transmission line is best, microstrip or coplanar waveguide?
In terms of I guess low insertion loss or low loss, then I think the coplanar waveguide is better at higher frequencies. But it may well be overkill or too expensive for some applications. So for some lower frequency applications, a microstrip is simpler, easier to manufacture, easier to lay out than an equivalent coplanar waveguide.
All right, well, thank you, Ian. That does look like all the time that we have for questions for today. Once again, if we didn't get to your question today, someone will be getting back to you after the program is over. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Once again, I'd like to thank Ian for his presentation and Q&A session today. Thank you for attending today's webinar, Best PCB Layout Practices for Frequency Synthesizers, brought to you by Tech Online, Analog Devices, and Richardson RFPD. On behalf of our guests and Analog Devices and Richardson RFPD, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.